All right, welcome back to the deep dive. Today we're diving into a paper that really caught our eye. It's called R10's aha moment in visual reasoning on a 2B non-SFT model.
Okay, yeah.
Now, I know that title might sound a little bit intimidating, but bear with us, because what we're talking about here is a potential breakthrough in how AI, especially AI that can deal with both images and text, can learn to reason.
Absolutely. And you know what's particularly exciting about this paper is that it's the first time, as far as I know, that researchers have been able to replicate this thing they're calling the aha moment. You know, that point where the system seems to have the sudden flash of insight and it leads to like demonstrably better reasoning.
And get this, they managed to do it with a model that's relatively small, just 2 billion parameters. And crucially, it's a model that hasn't been fine-tuned on a ton of labeled data. It's what they call a non-SFT model, meaning it hasn't had that extra layers instruction that's so common these days. And historically, getting this kind of like emergent reasoning, that aha moment, and longer, more thoughtful responses out of multimodal AI, well, it's been really tough.
Yeah, it's been a huge challenge. I mean, we've seen some progress with language models, but getting vision and language to work together in this way, it's a whole other ballgame.
For sure. So for our listeners out there, whether you're knee-deep in machine learning research or just curious about where AI is headed, stick with us.
Yeah, we'll break it all down.
We're going to unpack exactly what this aha moment looks like, why it matters, and why getting it to work on a smaller non-SFT model is such a big deal. Let's start with the basics. What do these researchers actually do? How do they set up this experiment?
Okay, so the core idea here is actually pretty elegant. They took this base model called Qwen2 VL2B. It's a relatively new vision language model, pretty efficient too. And it's already capable of understanding both images and text. What they did is they applied reinforcement learning directly to this base model.
So reinforcement learning, that's where you basically train the model by giving it rewards for good behavior, penalties for bad behavior.
Right, exactly. It's like training a dog, give it a treat when it does something right. And in this case, the treats were tied to the model's performance on spatial reasoning tasks. So things like understanding the relationships between objects and an image.
Ah, interesting.
And something pretty amazing happened. During training, the model started showing these signs of self-reflection, that aha moment, and it also started generating these longer, more well-thought-out responses.
So it's like instead of just spitting out a quick answer, it's actually pausing, considering different options, and then giving a more reasoned explanation.
Yeah, exactly. It's almost like it's thinking out loud, And the result of all this is that the model ended up significantly outperforming both the original base model and a version of the same model that had gone through this supervised fine-tuning, like we were talking about earlier. They tested it on this benchmark called CVBench, and the results were really impressive.
Okay, so they basically bypassed that traditional approach of feeding the model huge amounts of labeled data and showing it exactly how to reason visually. They just let it kind of figure things out on its own through trial and error, guided by this reward system.
That's right.
It's kind of like, I don't know, it reminds me of when a kid is learning to solve a puzzle. They might try a few pieces that don't fit, get frustrated, and then suddenly they see everything connects and it just clicks.
Yeah, that's a great analogy. And it speaks to the idea that maybe we can encourage these deeper levels of understanding in AI by giving them the space to explore and learn for themselves, rather than always hand-holding them with labeled data.
So this whole idea of the aha moment, this isn't something completely new, right? I seem to remember there was some earlier research with language models that showed something similar.
You're exactly right. This paper actually builds on the work that was done with DeepSeek R1. That was a language model, and it demonstrated some really impressive reasoning abilities when trained with reinforcement learning.
Right, I remember that.
And it also exhibited this aha moment phenomenon. But the key difference here is that DeepSeek R1 was a language-only model, while this research is focused on multimodal models, which, as we've discussed, is a much tougher nut to crack.
Yeah, for sure. And in the paper, they do a good job of putting this research into context. They talk about all this previous work on multimodal reasoning, and it's interesting to see how much of it has relied on either these massive labeled data sets or these very clever prompting techniques to try to coax reasoning out of these models.
Yeah, it's like they've been trying to find all these workarounds to get these models to reason. But what this paper is suggesting is maybe we don't need all those workarounds. Maybe we can let the models discover reasoning for themselves.
Right, and they specifically contrast their approach with DeepSeek R1, where the goal is to get this more autonomous development of reasoning through reinforcement learning. And there's this table in the paper, table 1, I think it is, where they compare their Visual Thinker R10 model to all these other attempts at replicating those DeepSeek R1 results in this multimodal setting. And they specifically highlight whether those other models showed that aha moment and that increase in response length.
Yeah, and it's pretty striking. For a lot of those other models, the answer is no. They just couldn't get those same emergent reasoning behaviors.
Okay, so let's talk about the nitty-gritty. How do they actually build and train this Visual Thinker R10 model? What were the nuts and bolts of their approach?
All right, so they started with that Qwen2 VL2B base model we talked about earlier. And for the reinforcement learning part, they used this algorithm called GRPO. It stands for Gradient Ratio Policy Optimization.
GRPO. Okay, I'm going to be honest, I'm not super familiar with that one. Can you break it down for us a bit?
Sure. So think of GRPO as this sort of fine-tuning mechanism that's really good at exploring all the different ways the model could generate its answers. It kind of lets the model experiment and try out different strategies, and then it uses those rewards to guide the model towards better and better reasoning.
Ah, I see. So it's not just telling the model what the right answer is, it's letting the model figure out how to get to the right answer on its own.
Exactly. And that's crucial because that's how we get that emergent reasoning, that aha moment. It's not something we can program directly. It has to come from the model itself.
Now, they also use this specific data set for training, right?
Right. They use the Spatial Aptitude Test dataset, or SAT for short. It's a VQA dataset, so visual question answering, specifically focused on spatial intelligence.
Okay, so the model is looking at images and trying to answer questions about the spatial relationships between objects in those images.
Exactly. And they actually designed this special chat template for the SAT dataset. It basically sets up this little dialogue where the model is acting as an assistant, and it's first prompted to think out loud to articulate its reasoning process.
I see.
And they even use this think tag to mark that part of the response.
Oh, interesting. So they're explicitly telling the model, hey, show us your work. Tell us how you're thinking about this.
Exactly. And then after the think section, the model gives the final answer, which is marked with the answer tag.
And the reward system, how did that work? Was it super complicated?
Actually, it was surprisingly simple. They gave the model a +1 reward for a correct final answer, another +1 if it used those think and answer tags properly, and 0 otherwise.
So no fancy scoring systems or anything like that. Just keep it simple.
Yeah, keep it simple. And that actually aligns with the approach that DeepSeek R1 took as well.
Interesting. Okay, so they've got the model, they've got the data set, they've got the reinforcement learning algorithm, and they've got the reward system. What about the actual training process? What did that look like?
Right. So for the experiments, they used 4 of these really powerful NVIDIA H100 GPUs. They trained the model for 1,500 steps. That might sound like a lot, but in the world of deep learning, it's actually pretty short.
Yeah, I was going to say, that seems relatively quick for training a model like this.
Right. And they use some specific hyperparameter settings, which they detail in table 2 of the paper if you want to get into the weeds.
Cool. We'll make sure to link to the paper in the show notes for our listeners who want to check that out.
Yeah, definitely.
But importantly, they didn't just evaluate the model on the data it was trained on.
Yeah.
They also tested it on CVBench, which, for those who might not know, is this really widely used benchmark for testing visual reasoning. And they also tested it on some other spatial reasoning data sets, like BLink and VSR. They wanted to make sure the model could actually generalize its reasoning abilities to new situations, not just memorize the training data.
And that's a really important point. We don't just want models that can parrot back what they've seen before. We want models that can actually understand and reason about the world.
Right. So what happened? Did it work? Did they actually see that aha moment and get better performance?
So the results were really promising. Table 3 and Figure 2 in the paper show that Visual Thinker R10 actually performed significantly better on CVBench, almost 60% accuracy.
Wow, that's a pretty big jump.
Yeah, it's a huge improvement compared to the base model, and even a little bit better than that SFT version we talked about.
That's impressive.
And they also saw improvements on those other data sets, BLink and VSR. But honestly, I think the most compelling evidence that something really interesting was happening is that they actually captured this aha moment in their training logs. They give this example where the model is trying to figure out if a certain object is above a doorway in an image, and it initially says therefore, dark brown wooden bed with white blanket is not above the doorway.
Okay, so far so good. Sounds like it's reasoning correctly.
But then get this, the model goes on to say, but wait, I can think of something else.
No way! That's incredible.
And then it goes into this think section and ends up revising its reasoning.
Wow, so it's like the model actually realized it made a mistake, or at least that it needed to consider another possibility.
Exactly. And that's the key here. It's not just about getting the right answer. It's about the model demonstrating this metacognitive awareness, this ability to reflect on its own thinking process.
Yeah, that's really cool. But they didn't just stop there, right? They also explored what happens when you try to apply this same approach to a model that has been fine-tuned on instructions.
Right. They wanted to know, does this whole aha moment thing still work if the model has already been kind of pre-programmed with a certain way of thinking? So they took that Qwen2 VL2B instruct model, the one that had gone through supervised fine-tuning, and they tried to apply the same GRPO algorithm to it.
Okay, so same setup, different starting point.
Yeah. And what they found was really interesting. On the one hand, they did see some improvements in performance, but the way the model was reasoning was very different. It started showing these, what they called trivial reasoning patterns.
Trivial reasoning patterns, what does that mean?
So like figure 3 in the paper gives a really good example of this. The question is, which object is closer to the camera? And the model's response is basically, think to determine which object is closer to the camera. I will measure the distance from the camera to each object, .think, and then it gives the correct answer. So on the surface, it looks like the model is reasoning, right? It's using that think tag, it's explaining its process, but the reasoning itself is so generic.
Yeah, it's not really engaging with the actual visual details of the image. It's just stating this very general principle.
Exactly, and that's what they mean by trivial. It's like, the model has learned to mimic the form of reasoning without actually doing the real cognitive work.
I see.
And this really intrigued them, so they dug deeper. They even tried freezing different parts of the model during the reinforcement learning phase. Like, they froze either the vision encoder or the language model just to see what would happen.
Wow, they really went all out.
They did. And surprisingly, they still saw performance improvements, but the responses were still those short, superficial ones.
So it seems like something about that initial supervised fine-tuning was really changing how the model learned through reinforcement learning.
That's right. It's like the fine-tuning was making the model less flexible, less able to explore those more nuanced reasoning strategies.
And it's not just that the responses were shorter. They also tried a really straightforward approach. They just said, okay, let's reward longer responses. Maybe that'll encourage the model to give us more detailed reasoning.
Right. They figured maybe if we incentivize the model to give us more, we'll get better reasoning.
Makes sense.
But unfortunately, that totally backfired. It led to what they call reward hacking, where the model just started generating these long strings of nonsensical text. Like, it was just trying to game the system, get those rewards without actually doing any meaningful reasoning.
That's funny. Figure 6 in the paper shows some examples of this, right?
Yeah, it's pretty hilarious. You can see the model just spitting out random words and phrases, trying to hit that length target.
So it seems like that whole idea of instruction fine-tuning, while it's great for making models better at following instructions, it might actually be a bit of a double-edged sword. It might be hindering their ability to discover those truly novel and sophisticated reasoning strategies on their own through reinforcement learning.
Yeah.
It's almost like we're teaching them the wrong kind of learning.
That's a really interesting way to put it. It's like we're giving them the answers before they've even had a chance to ask the questions.
Yeah.
And that might be closing off those avenues for them to develop that deeper understanding, that ability to think critically and creatively.
So the big question then is, what does this all mean for the future of AI?
Yeah, where do we go from here?
This research is really building on this growing movement to use reinforcement learning to push AI beyond those limitations of supervised learning. We saw this with Thinker R10 and its success with mathematical reasoning. But clearly, applying those same ideas to this world of multimodal data where images and text are interacting, it's presenting a whole new set of challenges.
Yeah. I mean, for so long, the dominant approach to building high-performing multimodal models has been to just throw more data at them, more labeled data. But this work is pointing towards a different path, a more autonomous path, where the models are actively involved in their own learning process.
And it highlights this really fascinating tension. On one hand, we have supervised fine-tuning, which is super effective at making models better at following instructions and doing specific tasks. But on the other hand, it might be limiting their potential to discover truly novel reasoning abilities through reinforcement learning.
Right. It's like a trade-off between efficiency and creativity. Supervised learning is efficient, but it might be stifling creativity.
Exactly. And the fact that they were able to replicate that aha moment on that non-SFT model, that really underscores the importance of letting these models explore and learn for themselves.
Yeah.
And it's not just about the aha moment itself. It's about what that moment represents. It's about the model being able to self-correct, to reconsider its own thinking. And that's a crucial step towards building truly intelligent AI.
Absolutely. And the fact that simply rewarding longer responses didn't work on those SFT models, that tells us that genuine reasoning isn't just about the length of the output. It's about the quality, the depth of thought behind it.
Okay, so where do we go from here? What are some of the potential research directions that this paper opens up?
That's a great question. And that's where we get to our novel notions segment, where we brainstorm some ideas for future research. So building on what we've discussed, I think one really interesting direction would be to systematically explore how different architectural choices in these multimodal models might affect their ability to develop this aha moment through reinforcement learning.
Interesting. So, like, what if we experimented with different types of visual encoders or different ways of fusing visual and textual information? Could certain architectures be inherently more conducive to this kind of autonomous learning?
Exactly. Maybe certain designs have these built-in advantages that make them more receptive to learning complex reasoning patterns from scratch through reinforcement learning. And if we can identify those advantages, that could have a big impact on how we design future AI systems.
Yeah, I like that.
And then another thought I had, especially given those challenges they faced with the SFT models, is what if we took a more curriculum-based approach to training? Instead of just throwing a fully fine-tuned model into this reinforcement learning environment, what if we started by training it on simpler reasoning tasks with more explicit feedback?
Mm-hmm.
And then we could gradually increase the complexity of the tasks and reduce the amount of direct supervision over time.
So almost like we're scaffolding the learning process, giving the model a strong foundation in basic reasoning before letting it loose to explore more complex concepts with reinforcement learning.
Exactly. The idea would be to see if we could mitigate those negative effects of that initial instruction fine-tuning by gradually guiding the model towards more exploratory, self-reflective reasoning.
I like it. It's like we're giving the model the tools it needs to think for itself, rather than just telling it what to think.
That's the goal, right? To build AI that can truly understand and reason about the world, not just follow our instructions.
Right. So let's wrap things up. Just to recap the key takeaways from our deep dive into R10's aha moment. Researchers have been able to replicate this fascinating phenomenon, this emergence of self-reflection, in a small, non-SFT multimodal model using reinforcement learning.
And they showed that this led to some really impressive improvements in visual reasoning.
But they also found that trying to apply those same RL techniques to models that had already been fine-tuned on instructions was a lot trickier.
Yeah, they often ended up with these very superficial reasoning patterns, even when performance improved.
And simply rewarding longer responses didn't work. It just led to the model trying to game the system.
Right.
Which raises this really important question. Does that initial teaching through supervised fine-tuning actually limit a model's ability to discover truly novel and sophisticated reasoning strategies on its own through reinforcement learning?
Yeah. Are we inadvertently hindering their creativity by giving them too much guidance early on?
A lot to think about. As always, we've got a link to the full paper in the show notes for anyone who wants to dive deeper.
Definitely check it out.
And for all our listeners out there, keep those brains buzzing. What other unexpected behaviors might we discover as we continue to push the boundaries of AI?
The possibilities are endless.
Thanks for joining us on The Deep Dive.
See you next time.